Hi everyone, my name is Kyle Cucci and I will be going through problem 8-10 in Fogler 4th edition. So to begin with, I'll just read off the problem statement and I'm going to do question A and B off of this and that is it. So the irreversible endothermic vapor phase reaction follows an elementary rate law of A goes to B plus C and is carried out adiabatically in a 500 decimeter cubed PFR. Species A is fed to the reactor at a rate of 10 moles per minute and a pressure of 2 atmosphere. An inert stream is also fed to the reactor at 2 atmosphere, as shown in figure P8-10b. This entrance temperature of both streams is 1100 Kelvin. So for part A, I'm going to derive an expression for CaO1 as a function of CaO and theta I. Also going to sketch out the conversion and temperature profiles for the case when no inerts are present. And then I'm also going to do this for when there's a moderate amount of inerts added and also for when there are a large amount of inerts added. Also sketch out a plot of the conversion as a function of theta I. So for part A, to derive Ca naught 1 as a function of Ca naught and theta I, you have A goes to B plus C. Using these base equations here for PFRs, we get that Ca is equal to C total times Fa over F total. And then each of those relating equations equals its counterparts for the feed. So we got C total is Ca plus Ci. We got F total is Fa plus Fi or inert. And then the sigma I in this case is going to be equal the feed of the inert over the feed of A. And then that comes down to the Ca naught 1 equation, and it all simplifies down to this right here in the box, Ca naught plus Ci naught over sigma I plus 1. So that's all there is for part 1. For part B, the graph the conversion and temperature profiles for different amounts of inert gas added. This can be done using polymath, and I'll elaborate on that later. I'll show you what you plug into polymath and what comes out, but for the most part, I'll just dive right in. So the initial conditions, 2 atmospheres, 1100 Kelvin, and a feed of 10 moles per minute. So for the mole balance here, this is the main equation you plug into polymath, and then you just have subsequent equations that feed back into that basically. So of course you have your rate law here, you have your concentration of A, and then in this part you have your epsilon, which ends up equaling 1 because of the original equation here, A goes to B plus C. T naught, of course, 1100 K. And then you also have your Ca naught equation, which you can just use the ideal gas equation, where it's your P initial over R and also over T initial. And then the profile for the temperature is also going to be this equation right here, and that can be found in the book. And then I'm just plugging in the um, relevant information for the substances that we are using here. And then so below we've got polymath. This is what it looks like when you plug it into polymath. So similar to what I've showed up here, just went into a little further depth so that it would work in the polymath program. So we got the mole balance here, and then your initial condition of X. You're starting at 0, and you want to see where you get to when you go to from 0 volume to 500 decimeters cubed. Initials right here again, and then for this case, C inert initial is also going to equal the C of A initial, and then theta I, or yeah, theta I right here this is what we're actually changing. So the problem statement wants to see this when it's equal to 0. So it doesn't want any inert going in. It wants a moderate amount. So that's this case, like I said, 10 to 1 ratio. And then the other case I did was for a theta of 100. So that's like we got a way more inert coming in than we do of A. And then FA naught, that's given in the problem statement, that's 10. And then, of course, our equation that derived in the beginning, and that is right here. So scroll back down here, and then epsilon, that's in here, and then we got the delta H and the CPs for both of the gases. And then again, the temperature profile, and then we also have the K equation that was given in the problem statement. And then we also have, well, we can derive the CA equation, and then by that we can write our rate law out. So this ends up going back into here. So that's what we really wanted, and T, it gets plugged into here, so on and so on. So anyways, ran that 3 different times, and then I made the graphs for both the conversion and the temperature profiles for each of them. So here it is for 0 inerts being entered. So as you can see, the conversion goes up very quickly with the volume, and then the temperature also drops rapidly. A moderate amount of inerts, and it starts to slow down. So it slows the reaction down. The temperature doesn't decrease as fast. And then for a high amount of inerts, we end up with, it pretty much, it doesn't stop the reaction, but it's pretty much not going anywhere. So the inerts end up just shutting off the reaction in general. And then this is also the conversion changing with the theta. So whatever you plug in, so we did 0 and 10. So you can see that 10 is like 90% conversion, and 0 is 40% conversion. And as you go higher and higher, like 100's probably way over here, and that's why this temperature profile here looks like that, and same with the conversion. And then this is just wanted to pull up the polymath report from this as well. So it just kind of shows you what went on, what it calculated, and really the main parts that matter are the initials. As long as you have those right and you have your equations right, the rest just kind of happens on its own. So again, we got one differential equation and then just a bunch of small equations. The big ones are the T, the K, and the rate. So this has been problem 8-10, A and B. Thanks for watching.